Time between failures in manufacturing system is an important practical KPI or key performance indicator for the health of manufacturing process and operation. To mathematically represent the problem and calculate the associated probabilities, a metric that is a parameter that is usually used is mean time between failures, or MTBF, which is the elapsed time between failures of a system during normal operation. Um, and that is a parameter of an exponential PDF or probability distribution function or probability density function, f of t, that is shown here, um, assuming that the manufacturing system follows such distribution, which practically is valid. So now imagine that we are trying to see what are the associated probabilities, as also highlighted here for this example. Suppose that the MTBF for an automated manufacturing system follows an exponential distribution with a mean of 2.5 days. What is the probability that such manufacturing system runs for more than 4 days without a failure, less than 1 day before any failure, more than 2 days but less than 3 days before a failure? So for 1, 2, 3 questions here, just to highlight, one correspond to which basically says more than 4 days. The area that is highlighted in green shade, that is the probability associated with question 1, which is the area under the exponential PDF curve, again highlighted in green. So we need to calculate that. Okay, so one question is, what is the probability that time between failure is going to be greater than 4 days? Okay, so since we are given the information that the mean time between failure in this system follows an exponential distribution, therefore we are going to just use the f of t equal to 1 over mu, which is the mean time between two events of failure, two consecutive events of failure, e to the minus time between failures divided by mu. And for this, of course, this is only valid, this PDF, for t greater than or equal 0. Since mu is given to us as 2.5 days, okay, we're going to apply it. Therefore, f of t becomes 1 over 2.5, which is 0.4 days, 0.4 rate, and then e to the minus t over 2.5, which becomes minus 0.4 t. So this is the probability density, the probability distribution function that we need to deal with for this example. Okay, so going back to here, of course, this is f of t, and we already know that the CDF, or cumulative probability distribution, so CDF or f of t is the integral, so it's just integral from 0 to t, f of, let's say, x dx. So in this case, we know the answer is 1 minus e to the minus 0.4 t if you just do a quick calculation of this using integral calculus. So you end up with this. For instance, when t is equal to 0, it means you're calculating the probability that the time between failure is equal to 0 or less than 0, which the answer is 1 minus 1. The answer is 0. So we're going to use this. This is effectively, so let's say if you say time is t0 up to t0, T0, what you're trying to say is what is the probability that time between two consecutive failure is less than or equal T0. Okay, so you need to use the complement. So 1 minus T less than or equal 4 days. Okay, so it's equal to 1 minus e to the minus 0.4 times 4. Okay, so this is equal to e to the negative 1.6. So that is the probability that in this system it will be 4 days gap between two consecutive failures. Okay, so next question. What is the probability that less than 1 day before the next failure? So that is the area corresponding to the orange shaded area under the PDF curve here shown. So time between 0 and 1, and we need to calculate the area, which effectively is the CDF of T0 equal to 1. So what you're saying here is we are interested to compute the probability of T less than or equal, it doesn't matter, we say equal. So say less than 1 day. Okay, so this means we are talking about 1 minus e to the minus 0.4, and time is 1 day. So the answer we get is 1 minus e to the minus 0.4. Okay, you can calculate that. And then the last part is asking that what is the chance, what is the probability that this time is going to be time between the two failures is going to be more than 2 days, but less than 3 days. So effectively what you're trying to compute is the probability that time is less than 3 days minus the probability that time is less than 2 days. Okay, so obviously this is equal to 1 minus e to the negative 0.4. I'm just going with the first here, this one. So times 3, okay, minus 1 minus e to the negative 0.4 times 2. So effectively, you can see and quickly compute that the answer is e to the negative 0.8 minus e to the negative 1.2. Okay, so that's the answer to part 3, and no wonder that you can see part 3, the probability computed in part 3, this probability, okay, correspond to the blue shaded area under the PDF curve. So that is part 3. Part 2 is the orange shaded area under the PDF curve, and part 1 is the green shaded area under the PDF curve. So that also visually give you an idea about the probability values. It's easy to see that since the width of these two areas for orange and blue is the same, the height for orange is higher, so therefore the probability computed in part 2 should be larger than the probability computed in part 3. So that's obvious. Okay, so I hope that this practical example provides some perspective and understanding of how we can use exponential PDF to compute the MTBF and to compute the time between failures in manufacturing systems.